So in this video, we're going to look for area and lengths in polar coordinates. So the first thing I want to look at is area. So if we look at the area of a circle, it's radius squared times pi. So if we want to look at an arc length, or the area of an arc, or a sector, we're going to use 1/2 r squared times pi. So that's going to give me the area of that section or the piece that I'm looking for. Now, that's if the radius is constant throughout it. We're going to look at it in terms of radius that's going to change based on a function. So when we're actually going through, we go through and do the formula out, the actual integration formula is quite simple. It's just the integral from a to b of 1/2 r squared times d theta. So if we look at this example here, we're going to find the area of an enclosed of one loop of a 4-leafed rose. So r equals cosine of 2 theta. Now, if I was to graph this out, and I would suggest using decimals to graph these problems out so you can see them, because visually being able to see what the graph looks like is very helpful to figure out where you're going to actually do your boundaries and stuff. So that one loop is done from pi over 4 to negative pi over 4, or negative pi over 4 to pi over 4, depending on how you want to do it. So that's the leaf that I'm going to look for. So the nice thing is once I find one leaf, I can actually just multiply it by 4 and I have the entire shape. So my integration is going to be from negative pi over 4 to pi over 4, 1/2 r squared. Now r is cosine of 2 theta. So I have cosine squared of 2 theta. We can't do the integration of cosine squared, so I've got to break it down. So I use the half angle formula, the 1 plus, so that's going to be 1 plus cosine of 4 theta. 1/2 times that. I can bring out the 1/2, and I'm going to do the integration of this piece in here. So the 1 becomes theta, the cosine 4 theta becomes 1/4 sine to the 4 theta. Now, notice how this is 0 to pi over 4, where originally it was negative pi over 4 to pi over 4. So since it's symmetric on the top and the bottom, I can cut it in half, and that's where that 1/2 disappeared to. So this 1/2 is the 1/2 that's out there. The original 1/2 is gone. So this is just looking at that top part of the leaf. Well, it's looking at the top half, and then since I'm doubling it, since I got rid of the 1/2, I'm looking at the whole thing. So I can just do it from 0 to pi over 4. Plug those in, and I get pi over 8. So that one leaf, that whole leaf that I was looking at originally, that leaf is pi over 8. So if I wanted the whole thing, it'd be pi over 8, plus pi over 8, plus pi over 8, plus pi over 8. So it'd be 4 pi over 8, or it'd be pi over 2 for the entire shape. So by looking for one leaf, using symmetry, I can figure out the whole one. So now we're going to look at finding arc length. And we're going to find the arc length of the cardioid that we did in the last section. So the equation, or the integration, is very similar to the one that we were using before. Remember, the parametric one was dx over dt plus dy over dt. This is going to be dx over d theta plus dy over d theta. And since the way it breaks down, it ends up being r squared plus dr over d theta. So it's the integral from a to b of the square root of r squared plus dr over d theta squared d theta. So we're going to use the cardioid. So in this case, it's r equals 1 plus sine theta. And we're going to do it from 0 to 2 pi. So we're going to go all the way around the shape. So r is 1 plus sine theta. So that goes in there for r. If I take the derivative of that, I get cosine. So I have 1 plus sine squared, or sine theta squared, and then plus cosine squared theta. So I can simplify this down a little bit and break it down. I'm going to get an integral from 0 to 2 pi of 2 plus 2 sine theta. Now, the problem is that it is very difficult to do the integration for, and sometimes it is. We're just not going to be able to do the integration out, even using all the rules and tricks and stuff that we know. So you can just use a computer to actually do some of the integration for this stuff. In this case, we use the integration to do it out, or the computer to do it out, and we find out that the length of the cardioid is equal to 8. So the big piece of this is making sure you know the formula, and then we're just going to plug the stuff into the formula to do the integration.